So, hello everyone again. This is lecture 4 part 1 of ray optics and optical instruments. In the previous lecture we completed the concept of power of a lens and the example related to power of a lens and the lens maker's lens equation basically. Today we will move on with the further discussions, a little just a recap in the starting, and then we will move on to combination of thin lenses, refraction through a prism and so on. So, I am Sameer Lavankar. Let us begin our discussion. Okay. So, for right now a course outline for you. So, we started with the introduction in which we understood the concepts of ray optics, that is first of all we are completely understanding this lecture as a discrete particle theory only, and ray optics has a ray of light has basically two things. The first is that the light is in the speed has a speed of 3 into 10 to the power 8 meter per second, and second is that light always travels in a straight line. Okay. After this, in the second point of reflection of light by spherical mirrors, we understood first of all the basic concepts such as what is focus, what is pole, what is principal axis and so on. Then basic two laws of reflection, that is angle of incidence is equal to angle of reflection, and the incidence ray, normal ray and the reflected ray always lies in the same plane. Then in the third concept of refraction, we understood the basic concept of refraction. What is this? So, basically a bending up of light when there is a change in the media is called as a is defined by a phenomena called as refraction. Then next in this also we also understood again two laws of refraction came. The first was that the incident ray, normal ray and the refracted ray always lies in the same plane, and the second was known as Snell's law of refraction, that is the ratio of the sine of angle I to angle R is constant, which is equal to n to 1, which is also called as refractive index of medium 2 with respect to medium 1. Okay. After refraction, we went to the total internal reflection concept, in which we understood that if we keep on increasing the angle of incidence from a denser to a rarer medium, there would be a critical angle of incidence denoted by IC, at which the angle of refraction would be 90 degrees. After that particular critical angle, if we increase the angle of incidence more, then we will find a phenomena such that the complete ray of light is incident in the same media only. There is no refraction happening, and hence there is internal reflection happening, and hence the phenomena is called as total internal reflection. Okay. So, this was your fourth point. Moving on to the fifth point, that is reflection at spherical surfaces and by lenses. So, in this concept we basically understood again sign conventions, which were also understood in second point, and then the derivation of lens maker's formula and the lens equation was being done. Right. Finally, in the last lecture we completed with the power of a lens concept, and a simple problem regarding the sign convention, power of a lens and lens equation was being explained. So, let us move on further with the today's discussion now. Okay, so this was the power of a lens. So, power of a lens is a measure of the convergence or divergence which is a lens introduces in the light falling on it. So, basically power is nothing but 1 by f, is denoted by 1 by f here, as you can see this is power of a lens and its unit is nothing but diopter. So, power of the lens is diopter. Okay. So, these all things are already explained to you. Moving on to the another concept. So, this was the examples which was being explained to you in the last lecture only. Now, let us move on to discussion, that is combination of thin lenses in contact. So, as the name suggests, what we are trying to do is we are arranging two different lenses very close to each other, and we are trying to find out if there is a change in the focal length, if there is a change in the power of the lens, etc. So, let us move on with the discussion. So, as you can see clearly that there are two lenses which are being placed in contact with each other, and we are trying to find out where the image is formed, what is the focal length, what is the power, etc. So, let us move on. Let me try to iterate line by line here. So, first of all, consider two lenses A and B of focal length f1 and f2 placed in contact with each other. So, quite evident, this let us denote this with a focal length f1 and let us denote this with a focal length f2. Okay, so these are two lenses of focal length f1 and f2 placed in contact with each other. Let the object be placed at a point O beyond the focus of the first lens A. That means the focus is in somewhere here, and we are putting the object beyond the focus, somewhere beyond the focus. The first lens produces an image at I1. So, let us assume that the image formed by this lens is formed at this location here, which is denoted by I1. Okay, so, this thing has been done. Now since image I1 is real, it serves as a virtual object for the second image B, because actually for final thing is we need to find out the image what is formed by the combination of lenses. So this can be assumed as the virtual object here. Okay. So since image I1 is real, it serves as a virtual object for the second lens B, producing the final image at I, quite evident. So finally using sign convention, when we derived it, we found that the final image by these two combination of lenses is nothing but image is formed at I, and hence you can see that this is V here, okay, and this is U here, quite evident. Okay, let us move on. So this thing is also been explained, and it must however be borne in mind that the formation of image by the first lens is presumed only to facilitate determination of the position of the final image, quite evident, because actually there is no such image I1 formed. It is only being understood so as to mathematically calculate the exact distance of the image from the what we can say lens. Okay, let us move on. So in fact, the direction of rays emerging from the first lens gets modified in accordance with the angle at which they strike the second lens, quite evident. So basically there would be a change somewhat here only. So and after the change happening, we can see that there is a imaging formed here. So the actual propagation of light won't be in this direction like this, it would have been, let us suppose, somewhere here, then moving in this direction here, and then deviating from its position, and then moving in this I direction here. So some sort of this would have happened. Since the lenses are thin, we assume the optical centers of the lenses to be coincident. Let this central point be denoted by P. So now what they are saying is that the optical center, they are, as the distance is very small, it is assumed that the optical distance P is same for the, or coincident for, that is coincident as in having the same point for both of these lenses. Okay. So this is denoted by P here. So this is again one denotation being done. So let us move on. Now just simple mathematical formulation of using the lens equation, and then finally we can find out the value of focal length and the power. Okay. So for the image formed by the first lens A, we get, so for the first lens A this, so basically simple lens formula, that is 1 by f1 is equal to, just let me write also so that I can explain it more clearly. So we know the lens equation. What is lens equation? Lens equation is 1 by f, which is equal to 1 by v minus 1 by u. Okay. So first of all, when we are doing it for the first lens, so as the focal length will be f1, the image formed will be v1, here, and u1 will be the object distance, quite evident. So this is the first equation which we have. Okay. Let us use the lens equation again for the what we can say, this equation for the B part here. So let us go on again. So now what we can say is again, so 1 by f is equal to 1 by v minus 1 by u. Okay, fine. Now we know that this is for the focal, for the second lens, therefore we will write it f2 here. Now here what will happen is we need to find out the value of image distance. What will be the image distance? Image distance will be v here, and what will be the object distance here? Object distance here will be equal to 1 by v1, because this is the image, this is the object, that it is this is the virtual object for the image which was formed by lens A. Okay, fine. So okay, for the image formed by the lens A we get, so this is for the first equation here, that is 1 by f1 is equal to 1 by v1 minus 1 by u1, and this is for the second equation here, that is 1 by f2 is equal to 1 by v minus 1 by v1. Okay, simple equations are there. Now just add both of these equations quite clearly. So you can see 1 by v1 and 1 minus 1 by v1 will get cancelled. Therefore what we will get, 1 by f1 plus 1 by f2 is equal to 1 by v minus 1 by u1. So what does this equation convey to you? This equation conveys to you that, let us suppose we have the lens equation again written, that is 1 by f is equal to 1 by v minus 1 by u1. Okay. So what was u1? u1 was basically the object distance. What is v? What is v? v is basically the image distance. So if we had some normal convex lens which is the which is analogous to these two different thin lenses, then the focal length of that lens would be equal to 1 by f1 plus 1 by f2. So just we need to compare both these equations, and we can find that what is the equivalent focal length. Equivalent focal length can be denoted as f, which is equal to product of f1 f2 upon summation f1 f2. Okay. So, this was again denotation. Let us move on, let us look over whatever is written here. So, first for the image formed by the first lens A, we get 1 by V1 is minus 1 by U is equal to 1 by F1, same as the first equation. Next, for the image formed by the first lens A, we get now for the second, we are putting the lens equation for the second lens here, hence we will get 1 by F2 is equal to 1 by V minus 1 by V1. Adding the above two equations, we will get 1 by V1 and 1 by U is equal to 1 by F1 plus 1 by F2, quite evident as I explained here also on the right hand side. Now, if the two lens system is regarded as equivalent to a single lens of focal length f, then we have 1 by v minus 1 by u is equal to 1 by f, and hence comparing these two equations we can get 1 by f is equal to 1 by f1 plus 1 by f2. Hence, this is the complete determination of what we can say summation of focal lengths for a combination of thin lenses. Okay, fine. Let us move on for the discussion. So, as we know what is power? Power is nothing but the reciprocal of the focal length. Hence, just using the similar concepts, we can find that power, equivalent power is nothing but equal to P1 plus P2 plus P3 dot dot till Pn. If there are summation of many what we can say focal lengths, then we can directly use the formula for P is equal to P1 plus P2 plus P3, and similarly for focal length we can use the formula 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3 dot dot dot. Okay, fine. Let us move on. So, next is the derivation is valid for any number of thin lenses in contact, as I already explained to you. So, if several thin lenses of focal length f1, f2, f3 dot dot are in contact, the effective focal length of their combination is given by 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3 plus dot 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 till 1 by fn. So, you can basically write here 1 by fn also. So, you can just keep on adding n number of focal lengths here, and hence you will get the answer. Okay, fine. So, this thing is also been explained. Next is in terms of power, above equation can be written as P is equal to P1 plus P2 plus P3 dot 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 till Pn. So, basically you can just add that this is equal to Pn. Okay. So, where P is the net power of the lens combination. Okay. Now, note that the sum in above equation is an algebraic sum of individual powers. So, some of the terms on the right hand side may be positive for convex lenses and some negative for concave lenses, quite evident. So, basically let us suppose we are using two lenses for convex, hence this will be positive, but if you are using something concave lenses here, then this will be negative. So, basically what would happen that if the equivalent power has to be calculated, it can be something like this, at 4 diopters plus 3 diopters minus 1.75 diopters and so on. This could happen. So, there can be algebraic summation or difference in the complete equation to be carried out. Okay, fine. So, this has also been explained. So, combination of lenses, what is the application of this thing now? So, combination of lenses helps to obtain diverging or converging lenses of desired magnification. It also enhances the sharpness of the image. So, basically the applications are, first of all, to find out to obtain diverging or converging lenses of desired magnification, and second is that it also enhances the sharpness of the image. Okay. So, this is the complete this is the complete what we can say determination, or this is the complete formulation of combination of thin lenses and contact. Okay, fine. So, this thing has also been explained. Next is about magnification. So, what does it happen about magnification? Since the image formed by the first lens becomes the object for the second, it implies that total magnification m of the combination is a product of magnification m1, m2, m3 till mn of individual lenses. What does it try to say is basically, so we know that magnification nothing but v by u, right. So, of what we need to find out, let us suppose that m1 is equal to, let us suppose v1 by u1. What is m2? m2 is basically v by v1. So, what we need to calculate actually? We need to calculate actually magnification. What will be the magnification? Magnification will be nothing but small v by small u1. How can we calculate it? Let us suppose we multiply these two equations. If we multiply these two equations, what we will get? V1 by u1 multiplied by v by v1. V1 u1 will get cancelled, hence we will get v by u1. What is this? This is nothing but the magnification which we require. Hence what we do is basically, if there are n number of lenses being kept intact, then what we do is we just multiply the magnifications for each of them. Hence, the complete magnification will be a product of the combination, product of the magnification of the complete combination. So, just iterating this again. So, since the image formed by the first lens becomes the object for the second, it implies that the total magnification m of the combination is a product of the magnifications, that is m1, m2, m3 dot dot for individual lenses. Hence, m is equal to m1 multiplied by m2 multiplied by m3 dot dot till multiplying interval mn. Fine, this thing has also been explained. Such a system of combination of lenses commonly used in designing lenses for cameras, microscopes, telescopes and other optical instruments. Fine, so this thing is also been explained. Let us move on to the another equation now. So, first of all, before going to the examples, let me just revise the complete concept again. So, whatever thing would be understood here is that the complete combination is 1 by f is equal to 1 by f1 plus 1 by f2 plus dot 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 till 1 by fn. Next thing what we got is p is equal to p1 plus p2 plus dot 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 till pn. And what is the magnification? Magnification nothing but m1 m2 dot 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 till mn. So, these are 3 instances which we obtained from this combination of thin lenses in contact. Fine, let us move on now. So, please look over to the question now. So, this is the basic example on combination of thin lenses only. There are 2 convex lenses, 1 concave lenses. Hence, when we try to derive the power, there will be 2 plus terms, 1 negative term, and let us see whatever the question is asking now. Okay, let us move on. So, first of all, find the position of the image formed by lens combination given in the figure. So, as you can see that first of all the object is placed here, that is at 30 centimeter location. First of all, it is a convex lens with focal length of plus 10, then there is a concave lens with a focal length of minus 10, and then there is a it is a half concave lens, as you can see. Okay, and then again it is a convex lens with plus for 30 centimeter location. As you can see that these are also being distant apart. So, what you have to do, you just need to find out the image formed by the combination of these lenses. Okay, let us move on now. So, image formed by first lens. So, image formed by first lens will be 1 by v1 minus 1 by u1 is equal to 1 by f1. So, just keep on writing everything. You know that by sign convention you have to write u as minus 30. Therefore, u for minus 30 will get you 1 by v1 is equal to 1 by 10 minus 1 by 30, hence v1 is equal to 15 centimeters. Okay. So, what does it say? That the image formed by the first lens serves as the object for the second, and this virtual object is nothing but at 15 centimeters from the first lens. Okay. As this 5 centimeter is being used, so now let me try to explain it much more clearly. So, this is 5 centimeters for you and this is another 10 centimeters for you. So, somewhere and at this location the image would have been formed for the first lens. Therefore, the complete virtual object distance for the second lens would be equal to not 15, but it will be 10 centimeters. Why? Because there is a distance between these two lenses. So, here we cannot directly use the concepts of 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3. Why? Because these two are not being intact apart. So, we cannot take into assumption that the point P is at the same is coincident here. Why? Because you can see that there are distances being given here, but you should know the basic concept, you should know the sign convention, you should know the lens formula, and then everything would be easy. Okay, let us move on. So, this is at a distance of 15 minus 5, that is 10 centimeters to the right of the second lens, quite evident. Now, again just using the lens equation, though the image is real, it serves as a virtual object for the second lens, which means that the rays appear to come from it from the second lens. So, again using the lens equation, so we know 1 by f, so we just wrote 1 by minus 10 here. So, let me just write so to make it more clear. So, 1 by f is equal to nothing but 1 by v minus 1 by u. So, it will be 1 by minus 10, which will be equal to 1 by v2, because we need to find out the image distance for the second image. Now, minus 1 by u. Now, what will be u here? U will be here 10. Why it will be 10? Because it is formed in the same direction as the transmission of light is happening, because we are measuring in the same direction as the transmission of light. So, just iterating mathematical formulation. So, you will finally get the value of v2. Now, for v3 what we will do, the virtual image is formed at an infinite distance to the left of the second lens. This acts as an object for the third lens. Hence, 1 by v3 minus 1 by u3 is equal to 1 by f3 or 1 by f3 is equal to this plus infinity 1 by this will be 1 by infinity, sorry, plus 1 by 30, hence v3 is equal to 30 centimeters. So, finally, what we got is that the final image is formed at 30 centimeters to the right of the third lens. Okay. So, hence this is clear. So, just iterating this again. So, basically this 1 by 10 minus 1 by 10 getting cancelled. So, v2 is equal to nothing but infinite distance. Just using this as an object for the third, we will get 1 by v3 is equal to 1 by infinity plus 1 by 30, 1 by infinity will be 0, hence v3 is equal to 30 centimeters. So, final formulation, final conclusion of this question is that the final image is formed 30 centimeters to the right of the third lens. So, that means it is formed somewhere here. That means from the first lens it is formed at a distance of 30 plus 15, that is 45 centimeters. From the second lens it is formed at a distance of 30 plus 15, that is 40 centimeters, and from the third lens it is formed at a distance of 30 centimeters towards the right of the lens, right, the third lens. Okay. Let me stop it here only. In the next lecture I will start with the concept of refraction through a prism. Okay, so thank you so much.